Hello everyone and welcome to another video. So today I wanted to have a real quick discussion talking a little bit about basic probability. So this is going to be the first video in a series of videos where we are going to talk about probability and statistics. So today we're just going to have a quick introduction on some of the core concepts, but later we're going to build on this foundation and talk about things like probability distributions, Gaussian and normal functions, and a lot of other topics. So we're just laying the framework today, so this is going to be a little bit of a quicker, more basic discussion. So why don't we just go ahead and just jump right in. So you really can't talk about probability without start talking about things like statistics and data sets. So let's say that we've got some set of data here. This is maybe the range of temperature measurements every day over a month. So this is 30 data points of temperatures, right? So in Fahrenheit, and you can see this is probably the summer or spring months. It's a little bit warmer temperatures. So some of the things that you might want to do very first is so go ahead and sort this. This is going to help us a lot. If we take this 30 numbers and we sort them from lowest to highest, we'll end up with a list that looks like this. So we see the minimum temperature is around 77 and the maximum temperature is about 99 degrees Fahrenheit, right? And then you've got a whole bunch of temperatures in between. So some of the things you might want to do with this set is characterize it or visualize it or just get a better understanding of what does this data look like and how can we parameterize it. So one of the very most popular ways to visualize a data set like this is what's known as a histogram. So a histogram, all you do is you take the data here and we're going to put them in bins. So we're going to define these bins. So we're going to start here at 75 to 80. Let's make a bin where any temperature that falls between that is greater than or equal to 75 but less than 80, let's count how many times that occurs in this data set. So in this case, you can see that that's 1, 2, 3. These three data sets or data points fall in this bin. So we are going to say that there are 3 data points within this bin. Then we're just going to move to the next bin. The next bin is for temperatures that are greater than or equal to 80, but strictly less than 85, right? So again, you just keep counting this and you'll see that there are 7 data points like that. And then away you go in these bins, right? And again, the size and dimensions and widths of these bins are somewhat arbitrary. In this case, we just picked these because it happens to work nicely, but depending on whatever computer program you're using, you should be able to specify the width of your bins to your heart's content, right? So we end up with a distribution that looks like this. So what this histogram is showing you is that a lot of data points seem to fall between 85 and 90, and you really don't get too many data points or days that are very far away from this middle-ish average type of value, right? So the histogram is a real easy way to visualize what this data looks like in terms of where the average is, as well as how far this data is spread, right? This thing could be fatter or it could be a lot shorter and narrower, right? So instead of using these terms like fatter, shorter, and narrower, let's come up with some quantitative metrics that can help us understand and parameterize this distribution or this set of data. So one of the easiest things you can do with a set of data is calculate what's called the median. Right? And all the median is, it's an idea of the quote-unquote middle of the data set. So let's define it here. The median, it's really, it's literally the middlemost data point of this sorted data set if the number of samples you have is even, but, if it's odd. But if it's even, there isn't an actual, direct middle sample. So instead what we're going to do is we're going to take the average of the 2 middlemost points in that case. So for our data set, we actually fall into this case where it's even because there are 30 data points. So we have to go look at the very 2 middlemost values. That's the 15th and 16th values, right? And then just take their average. So in our case, the median is 87.5. So what this does is it literally tries to tell you and put a finger in the exact sort of middle of the data set. There should be an equal number of samples above that number and an equal number of samples below that number, right? So that's sometimes referred to as the median, right? Now, the range of the data set is another very easy quantity to measure, right? It's basically the largest value minus the lowest value. So it gives you an idea of the range of measurements of numbers. So in our case, you can see it's just 99 minus 77. So there's a range of 22 degrees in this data set, right? So this is one way that you can kind of characterize sort of the middle of the data and as well as how wide the data is spread. Right? Now, that being said, these are not typically the parameters or the values that you may want to calculate for a lot of these distributions. Instead, we might want to look at things that are a little bit more sophisticated. So for example, one of these things is what's known as the interquartile range, or IQR. So all the IQR is we're actually going to compute the median of the data above the median, and then we're going to compute the median of the data below the median. So in other words, let's look at this QU, right? So all you do to get QU is you go ahead and you find the median, right? Which we said was somewhere here in the middle. What was it? The middle was 87.5. So I think it was like, you know, here, right? Okay, and then we're going to compute the median of all the data above this, right? So if you do that, you get this as 89, right? And then we're going to compute the median of all the data points below the median. That's this other data here, right? And we're going to put our finger in the middle there, and that is 80, where was it? Oh yeah, 83, right? So here, the interquartile range, it's just the difference of those two medians. So in this case, it's 6 degrees. So again, this is another way that's trying to help measure the spread of the data or the thickness or the wideness of the distribution, right? Now, the real way that you're probably going to want to do this, you're going to want to look at things that are called the mean and the standard deviation / variance. So let's talk about those now. So the mean, this is pretty darn simple. This is the statistical average of your data set, right? So all it is, you're just going to sum up all of the values in your data set and then divide by the number of data points you have in your data set, right? So this is the sort of the average, the mathematical average of the data set, right? So in this case, we get 86.67-ish, something like that, right? So you see that the mean is not necessarily equal to the median, right? Depending on how this is distributed, these things will usually be, you know, somewhat close, but a lot of times the mean is a better measurement of the quote-unquote middle or average or center of your data, right? Now, once you have the mean, you can calculate what's known as the standard deviation and the variance. And these two things are very closely related. In fact, the standard deviation is typically denoted as sigma. The variance is just sigma squared. So again, you might think these two things are different, but really they're just related directly one to another by a square term, right? So again, the variance is nothing more than standard deviation squared, right? So the way that you're going to compute this is it's a little bit interesting, but let's look at this bottom formulation here, because this is the one that I think most people are typically familiar with, right? All you're going to do is you're going to sum up the data set, and you're going to take each sample in your data set, see how far away it is from the mean of the data set, and square that, and then just add it all up, and then at the end of the day, divide by the number of samples, right? Now, the only thing that's slightly different here is usually you'll see this formula, right? But for smaller data sets, if n is small, if n is like 5 or 10 samples, sometimes the normalizer in front, you don't divide by 1 over the number of samples. It's 1 over the number of samples minus 1. So again, this is a very small difference, right, depending on the size of your data set. But just be aware of this. Some mathematical packages, for example, like Mathematica, use this formulation rather than this formulation. And again, the difference is fairly small. Now, all this is going to do, we're going to see later, is that the mean, right, kind of helps you understand where the middle of this distribution or this data is. It's sort of like an average value, right? So this is going to give you something like the mean will tell you where this is. And what the standard deviation is going to show, we'll talk about this later, is it shows you sort of the width of this distribution. Okay? So if you had a distribution that looked like this versus this, you can see both of these have the same mean, right, or the same average, right? But you could potentially have different widths of this distribution, right? So here, these sigma 1 and these sigma 2 could be different, where sigma 2 is bigger than sigma 1. And again, we're going to look into this a little bit later, but we just wanted to define all of these terms right now, so we'll have the framework in place when we want to start looking at these for specific different types of distributions down the road, okay? All right, so I think that sets us up fairly nicely. Why don't you give me a second to erase the board, and we'll move on to our next topic. All right, so now let's start working our way up to discussing probability. So to get there, let's first talk a little bit about a couple of definitions. So let's talk about an experiment. So if you have an experiment, this is basically some process of measurement or observation. This could be something like you're doing in a factory, or as we're going to see later, it could be something as simple as maybe just even, you know, rolling a fair 6-sided die, okay? Within an experiment, you can have a trial. So a trial is just basically performing the experiment once. And when you do that trial, you're going to have some outcome, right? That one trial is going to produce some results. So the outcome is basically a result of that trial. Sometimes it's also known as a sample point. And the reason it's called a sample point sometimes is that if we consider the sample space of this entire experiment to be basically a set of all possible outcomes of this experiment, right? So with those definitions in mind, let's look at an example, as we said, where an experiment is just, you're going to roll a fair 6-sided die, and we want to see what happens. So a trial of this might be one single roll, and an outcome in this case, you know, maybe you get a 2, right? That's what you end up with. Now, the sample space for this experiment is what could possibly happen as you roll this die. Well, obviously, 1, 2, 3, 4, 5, or 6 can come out, right? That's the only possible outcomes. Now, within this framework, we can also define separate subsets known as events. So, for example, let's call event A just being the set of 1, 3, 5, meaning you roll an odd number. Another event, B, might be 2, 4, 6, which is rolling an even number. You can even have random numbers or random events, like event C is just 1 or 2, and that event could be, rolling a 1 or a 2, or rolling less than 3, however you want to think about it, right? So you can have all of these different events. Now, in this context, what we like to say is that if an outcome is in any of these sets, those subsequent sets have said to have occurred, right? These events have occurred. So in this case, when you roll a 2, both event B and event C have both simultaneously occurred, right? Now, we see that we're going to be looking at this in terms of set theory, so a lot of framework and tools that you use to working with sets can also be used in this framework. So for example, you can talk about the union of two sets. So if you have a set A and B, and you take their union, sometimes referred to as this big sort of cup-looking feature, what that's defined as is all of the points that are in either A or B, right? So I like to think of these in terms of Venn diagrams. So if you draw a Venn diagram of this, so S is the entire sample space of all possible outcomes. A is this oval up here. B is this oval down here. And then A union B is basically all of the points that are either in A or B, which is all of these hash mark blue lines, right? Now, contrast that with the intersection operator, A intersect B. And again, this intersection operator is sort of this big cap, sort of looking upside down U, right? That's the symbol for it. And all this denotes is all of the points that are in A and B, right? So that's the only difference, right? And again, the Venn diagram perspective, you can see that what we end up with is A intersect B is where the two sets overlap, right? The points that are in both sets simultaneously, right? Now, this intersection thing is interesting because it allows us to define some other concepts. So what happens if A and B don't have any points in common? If they don't have any points in common, then the intersection is actually the empty set, right? There are no points in either one of those two sets, right? If that's the case, these events A and B are sometimes referred to as mutually exclusive, meaning if something occurred in A, it cannot happen in B, right? So if A occurred, B cannot occur, and vice versa, right? And then lastly, there's this idea of a complement, right, to a set. So denoted by the superscript C, if you have a complement of a set A, that's basically describing all of the points in S that are not in A. Okay, so what you basically end up with is you can have things like A intersect with A complement is obviously the empty set, right? Because what happens there is that you basically take a set A and then you try to intersect it with everything that's not in that set. Obviously, there's nothing left, right? That's an empty set. And similarly, if you take A union A complement, you get the entire sample space S, okay? All right, so with that in mind, again, let me erase the board and we'll move on to using this in discussing and building up our probability ideas. All right, so now we're really ready to tackle the idea of probability in a formal sense. So let's look at it in a couple of definitions. So the first definition is, let's consider a situation where you have a sample space S where all of the points are equally likely to occur. If that's the case, then what you can do is define the probability of an event A as basically just being the number of points in A divided by the number of points in the entire sample space S, right? So hopefully that makes good sense. Again, if each of these points are equally likely, right? That's the key underlying term in this definition here, right? So what immediately follows out from this definition, obviously, is that the probability of something happening in the sample space is 1, right? It's guaranteed to happen, and hopefully that's a little bit of a no-duh kind of moment, right? Now, what's interesting is let's start thinking about this. What if S is too large to kind of enumerate in a reasonable fashion, right? In that case, it might be easier, instead of discussing these probabilities directly, is let's talk about what's known as a relative frequency. So if you just conduct an experiment for a lot of trials, right, you can define the relative frequency that event A occurs at as basically the number of times this event A happens divided by the number of trials, right? So again, that makes perfectly good sense. If you just do an experiment a whole bunch of times, right, execute a whole bunch of trials, you just need to count how many times did event A happen divided by the number of times you executed that experiment, right? Now, what's interesting about this is if you think about this in combination with our set theory discussion earlier, if you look at the relative frequency of events A union B, right, this should happen to be the sum of the relative frequency of event A plus the relative frequency of B if A and B are mutually exclusive, right? If they don't overlap each other, you should be able to do this, right? Okay, so that's great. Let's now extend this to kind of a more general case. Let's look at this second definition of probability, right? So for every subset A in the sample space, right? So this is just some event A. It could be small, it could be large, whatever. It's just a subset of S, right? So for every set A that is inside of S, you can find and associate a number. Let's call it P of A. And this is going to be, and again, in the back of your head, just think probability of this event A, right? We're going to define this P of A such that several things happen, right? One is that this P of A has to be between 0 and 1, okay? That's pretty simple. The other one is that, as we talked about earlier, the probability of S, if you take A to be equal to S, right, the entire sample space, that's got to be 1. And then, just like we said earlier, for mutually exclusive events, right, the probability of event A union B, it's just the probability of A plus the probability of B if A and B are mutually exclusive, right? So you can see the parallels between this idea of a relative frequency of just basically an experimental idea or experimental computation of relative frequencies versus a kind of more formal definition, right? This is kind of from the probability definition standpoint. So if we buy into these three items, we can basically cook up a couple of theorems that are associated with probability, right? So first one is, let's look at the idea of a complementary event, right? So the probability of A complement, right, is just 1 minus the probability of A, right? And again, I'll let you chew on that a little while, then hopefully that should make pretty reasonable sense, right? The second one is building off of this idea of mutually exclusive events, right? So if you have all of these events, A1, A2, all the way up to AM, and if all of them are mutually exclusive, meaning there are no overlaps, right, then the probability of the union event is just the sum of the individual probabilities. Again, this is for mutually exclusive events, right? Now, what about if you have events which are not necessarily mutually exclusive? That leads us to theorem number 3. So if you have two events A and B which are not necessarily mutually exclusive, then the probability of A union B, it's the sum of probability A plus probability B, but then you have to subtract out the intersection of the two. And what might make sense is if you look here at this picture, let's look at it right here. So here we have A and B, two events which are not mutually exclusive, right? So the probability of A, you can kind of think of as this red hash mark area, right? And then the probability of B is sort of the blue hash marked area, right? And now what you end up with is the probability of A or B, right? It's this area which is red or blue, right? So it's the probability of A, which was kind of, you can think of the area of the red, plus the probability of B, which is the area of the blue. But then we have to subtract out the intersection here. This is A intersect B, right? So we don't double count the area in our probability calculation, right? So this is the picture that goes along with this, right? Okay, so with this framework in mind, yeah, let me erase the board and we will now go ahead and take a look at another related concept. All right, so this brings us to the topic of conditional probability and independent events. So let's tackle the conditional probability first. So let's say that if you have the probability of an event B, under the condition that event A has occurred, this is called the conditional probability of B given A, denoted as such, right? So here's a probability that B occurs given that A has occurred. And the picture that goes along with this, again, we can look at this Venn diagram down here. Let's say you've got the sample space S, you've got event A, B, heck, you might even have things like C, D, E, any of those things like that, right? Now, what we're interested in is if you first say, well, what's the probability of B? You can see that it's just this, right? This area. Maybe let's do this in, I think we were using blue earlier, blue kind of cross hatching, right? Okay. That's this area, right? But now what's interesting is we're not just interested in this area, because what we want to look at is we want to ask, what's the probability of B given the fact that I know for a fact that A has occurred, right? So A is over here, right? This is event A, right? So if you look at this picture long enough, you can see that, okay, I know A has occurred. So this event A has happened. What's the probability that B happened at the same time, right? You can see that that's this overlapped area of red and blue cross hatching here, right? So this area of red and blue cross hatching, again, using our set theory, we can see this is A intersected with B, right? So if I know that this A event has happened, the probability that B happened at the same time, it's this area divided by the entire area of A, right? So really, this conditional probability of B occurring if A has already occurred, it's the area, it's the intersection, right? It's a probability of A intersect B divided by sort of the now area of A, or the probability of A, as you can see over here, right? So this is the conditional probability, right? And you can flip this around easily. If you're looking for the probability of A given that B has occurred, right? It's the same idea, it's just sort of flipped vice versa. So it's the probability of still A intersect B, or B intersect A, however you want to think about it, right? But now the denominator is probability of B, right? So let's save these two ideas here, these two equations. We're going to come back to them in a second, right? Let's look at an example of where this might be useful, right? So let's say we've got a family over here, okay? And I'm interested in the composition of the family. In fact, this sort of mirrors my family. So I actually have two kids, okay? I have two children, a child 1 and a child 2. Now, I'm not going to tell you right now if this is a boy or a girl and this is a boy or a girl. Instead, let's ask ourselves 3 questions. So the first question is, what's the probability that my first child, child 1, is a girl? Right? So let's tackle that right now. This is pretty trivial, right? Let's ignore child 2 for now. I'm just asking, is this a boy or a girl? Right? Which one is it? Right? And if you think about this, well, you don't have to think about this very long, right? This is basically a coin toss. Let's assume that boys and girls are born with equal likeliness, right? And now I'm asking, what's the probability that this is a girl? This is literally flipping a coin, right? So the answer to this is just a half, right? Okay, that's pretty darn simple. Okay, now let's look at the second question. Okay, what's the probability that both children are girls, right? So what is the probability that I have 2 kids in my household? That's all I'm asking. So the way we can tackle this is, let's go ahead and just enumerate the sample space S, right? So in this case, S, right, what are all the possible makeups? Luckily, this problem is small enough that we can enumerate all of the possibilities. So I could have a boy and a boy, right? I could have a boy and a girl. I could have a girl first, then a boy, and then I could have a girl and a girl, right? So here's the sample space S, right? And now, assuming, again, that this is all equally likely, again, this is now like flipping 2 coins in a row, right? Flip a coin, then flip another coin, right? Because I'm looking for this, right? So all of these outcomes are equally likely, so I think everyone would agree. In this case, for problem question number 2, the probability is 1/4, right? Okay, so there's a 1/4% chance. If you just ask me this question, what's the probability that I have 2 girls in my family? A quarter of the time, 25% of the time, that would be true. I would have 2 girls, okay? Now, let's look at this one. This is question 3. Now, ignore the first part of the question, right? If you ignore the first part of the question, this is the same as question 2, right? Look at the second sentence of this problem. It says, what is the probability that both children are girls? That's exactly what we just did in question number 2, right? Now, the twist on this is, now I'm going to give you a little bit more information, right? What if I told you that one of my children are a girl? I have 1 girl. Now, I want to basically ask kind of question 2, with the understanding that this has occurred, right? That I have at least 1 child that is a girl in my family. This is really interesting because just the way that we pose the question now, by giving you this other bit of information, does that change the answer, right? Does this change this probability from 1/4 to something else, right? Just this first sentence here, does that actually matter? Right? Well, if you think about this long enough from the perspective of conditional probability, the way we can look at this here is, let's go ahead and define ourselves another event E. Let's say my event E is the event that the family has a girl. Has a girl. Right? Okay? Now, this event E, if you think about this, how can this possibly happen? What has to happen for event E to occur? Well, you could have a boy and a girl. You could have a girl first, then a boy, or you could have a girl and a girl, right? This is what sample set E looks like, right? So what we're looking for now is, I want to know what's the probability that both of them are girls, okay? So let's define another event F, right? Which is family has both girls, right? So this event is just GG, right? this sample size, or this set, or this event, this is the only way this occurs, right? Now, in the context of this problem, what we're looking for is I'm looking for the probability that the family has 2 girls, F, given the fact that I know that event E has occurred, right? I know the family has at least a girl, a single girl, right? One of the children is a girl, right? Sorry, and I probably should have said, I think I wrote this out. That at least, sorry, this should say at least one of the children is a girl, right? What's the probability that both are girls, right? Okay, so in this case, right, you plug this into our conditional probability. This is the probability of F intersected with E, right, divided by the probability of E, right? Okay, so now, if you look at this, what is, let's look for this set F intersect E, right? That's what we're looking for, right? So it's this set intersected with this set. The only common one is GG, right? So this is GG, right? Okay, so really this, I ran out of white space. Maybe I should do this calculation over here, right? Let me come over here, see if we can do this. So the probability of the numerator of this set, it's really, what's the probability of GG occurring, right? This is the set F intersect E, right? Divided by the probability of set E, event E, which was the family has at least a girl, right? And maybe, again, I should write this in. Family has at least a girl, right? So this is the set of, what was E here? Okay, it was BG, GB, or GG, 2 girls, right? Okay, so again, now we ask ourselves, what's the probability of just girl, girl, right? Well, we answered that already in question 2. This is 1/4, right? So the numerator is 1/4, and the denominator is, what's this probability? This, right, again, if you come back to our original full sample set, right, we saw that this is equally likely. So this is what, 3/4, right? So the answer is actually 1/4 divided by 3/4, which comes out to just 1/3, right? So that's interesting here in the sense that this extra bit of information changes the probability from 1/4 to 1/3 due to this idea of conditional probability, right? And again, this might be going clang in your head, and you might be saying, no way, there's no way this is actually true. How can you change the probability by just giving me, by revealing additional information? Well, it absolutely is true. In fact, here's the output of a MATLAB script. In fact, I'll make this MATLAB script available for download on this on the description of this video. This is a simulation that I ran for, I can't remember, I think it was 20,000 trials of this using these conditions. And as you can see, all of these probabilities check out in simulation, right? And this actually, while we're talking about this, this is very closely related to what's referred to as sometimes as the Monty Hall problem. I encourage you to actually go look that up because that's another very interesting probability topic and example of using conditional probability in interesting situations. Okay, so that's good. Let's go ahead and talk about what we can use this conditional probability for. All right, so let's look at this again, these conditional probabilities. And in fact, what I want to do is let's solve for this probability of A intersect B, right? So if you do this here, you can easily see the probability of A intersect B is just going to be what? It's the probability of A times the probability of B given A, right? And then same thing down here, you could also do the exact same thing. You could solve for probability of A intersect B, and that's just going to be the what? It's the probability of B times the probability of A given B, right? So this leads to theorem 4, which is kind of referred to as the multiplication rule, which is basically stating that exact fact, right? It's the probability of the intersection of A and B. It's just given by this phrase, this expression, or this expression, either one. Kind of pick your poison, right? So let's look at an example of that. Let's say that you've got a factory that is producing, screws. Okay, now there's 2 possible things that might happen in terms of defects for these screws. Like you could have defect A, which is the screw is too slim, or you could have defect B, the screw is too short. And you could probably have both of those at the same time, right? So let's say that we know from quality control that the probability that a random screw is too slim is 10%, right? And now, of those screws that are too slim, you know that the probability that those screws, the ones that are already too slim, they are also too short, that probability is 0.2 or 20%, right? Now the question is, okay, if we go back and pick a random screw out of the production bin, what's the probability that it is going to be both too slim and too short, right? So all we need to do is basically identify what do these numbers mean in the context of our conditional probability, right? So this first one I think is pretty easy, right? This stat here that says the probability the screw is too slim is 10%. What is the too slim event? It's A, right? Probability of event A is 0.1, right? Now this one, this second piece of information is telling us the probability that it is going to be too short, right? Given the fact that it is already, we know that these are slim screws, right? This is 0.2, right? Now we need to ask ourselves this. We want to know what is the probability that a random screw is both too slim and too short. Well, that means we're seeking the probability that it is too slim and too short, or A intersect B, right? That's what we're looking for. So we want probability of A intersect B, and we can go ahead and apply our multiplication rule here. So we just got to figure out which one is the right one we want. It's basically this form, right? It's the probability of A times the probability of B given A, right? Because that is exactly what we have here. So this is 0.1 times 0.2. Right, that's what we have, and then this ends up as 0.02. So there you go. So 2% of all, whoops, no, I should, 0.02, this is 2%, right? So 2%, right, of the screws are going to be total failures, right? They're going to be both too slim and too short. All right, so now that we've talked about conditional probability and this idea of the multiplication rule for probabilities, let's turn our attention to the second half of this statement and take a look at what are known as independent events. So if you have two events A and B such that the probability of A intersect B is equal to the probability of A multiplied by the probability of B, then in this case, when this is true, A and B are referred to as independent events. Now, we can understand the physical meaning of why they're called independent by examining this conditional probability expression that I left up. So again, let's take a look at our conditional probability of B given that A has occurred, right? And we said that that's probability of A intersect B divided by the probability of A. Now, let's assume what happens if A and B are independent, right? If that's true, then we note that this numerator here, this is just given a probability A times probability of B. So I have probability of A times the probability of B. That's the numerator of the expression, divided by the denominator is just probability of A. So you can see that this probability of A cancels, and what we end up with here is the probability of B given A is equal to the probability of B. Okay? So in other words, if you think about this long enough, what this is saying is that the probability of B, given that A has occurred, is still just a probability of B. So the fact that event A occurred told you nothing about the probability. It did not influence the situation at all. So B is going to happen completely irregardless or independently of A, right? A tells you nothing about this scenario, right? And you can do the exact same thing for our other expression where you look at the exact same analysis and look at, I want to understand what is the probability of A given that B has occurred, and you'll end up with the exact same thing. This is now probability of A. So in this case, the fact that event B occurred told you nothing about event A, right? So that's the idea of independent events. And again, you can extend this for multiple situations. If you have an A1, A2, right, all the way up to AM, these can be independent. Basically, if you have the probability of A1 intersect A2 intersect intersect AM is equal to basically the product of all of these probabilities. Probability of A1 times A2 times probability of AM, right? So then in this case, all these are independent events, right? Now, one thing that we might want to have a quick slight side discussion on is note that a lot of times some people may incorrectly interchangeably use the idea of mutually exclusive and independent events. Some people think those are the same thing, and actually we should make sure that we understand that they are not, right? So in fact, the two are opposite of each other. Independent is not equal to mutually exclusive. Right? So if you remember, right, the idea with mutually exclusive is that if one of them occurred, right, so mutually exclusive, the definition was A intersect B was the empty set, right? Therefore, the probability of A intersect B is equal to 0, right? This was the idea of mutually exclusive, right? And you can clearly see that that is not the same thing as this, right? So that's mathematically, you can show that the two are not the same. Again, but conceptually, it's almost even easier. We said independent events, what that means is that the fact that one of the events occurring does not tell you anything about the other event. Mutually exclusive is almost the exact opposite extreme, right? The fact that one of these events occurred tells you everything you need to know about the other event, namely that it cannot occur, right? So again, independent and mutually exclusive are not the same. They are actually almost like polar opposites of one another, right? So let's take a quick look at an example of independent events. And in fact, we can revisit that example we were talking about earlier where we had the family of girls, right? Let's recall question number 2, right? Question 2 was, what's the probability that both children are girls, child 1 and child 2, right? So we can do this using our independent event concept by defining two events. Event A is that child number 1 is a girl, and event B is that child number 2 is a girl. Now, we know that these two events are independent of one another, right? When asked just in a vacuum like this is basically the equivalent of flipping two coins. The second coin flip has nothing to do with the first coin flip and vice versa. Therefore, the probability of child 1 being a girl is a half. Probability of child 2 being a girl is a half. So since those two events are independent, we can look at the probability of A intersect B, which is now child 1 and child 2 are girls. And we get that now just using our multiplication rule like we saw earlier. So it's a half times a half, which is a quarter, which is the exact same answer we got when we just simply enumerated the sample space, right? The other thing that we might want to talk about real quick is, let's think about a Venn diagram of this picture. So you can look at, event A, right? Let's maybe do event A in sort of red cross-hatching, right? So this is child 1 is a girl. So that's this here, right? So girl, girl. So this is event A, right? And then event B, let's do this in blue cross-hatching in sort of the other direction. So blue is like this, right? So this is child 2 is a girl, so that's the girl, girl. So that's this here, right? Okay, so clearly you can see in this case, the Venn diagrams, they overlap, right? Even though the events are independent, excuse me, there is overlap, right? And what we see is the overlap is in such a fashion that this area rule, so to speak, is enforced, right? Namely, the area of the intersection, which is down here, right, is equal to this area times that area. So again, it looks like a half times a half gets you a quarter, right? So there you go. That's the idea of independent events. All right, so the last thing I want to cover today is this law of total probability. So the way this works is, let's go ahead and consider a sample space S, and then we're going to partition this space into this partition denoted Bn, where n can go from 1 to however many partitions that you'd like. So in other words, the idea with a partition is that you have a set of disjoint events, right? So these events, B1, B2, B3, they're not overlapping in any way, right? And their union altogether form the entire space. So this is what we mean by partitioning the sample space S. We're basically going to break it up into n different sets or events, which are all mutually exclusive from one another, right? Okay, so in this case, what's interesting now is we can now consider any other event. In fact, let's go ahead and draw this in green. Maybe I'll do it like this. Let's call some other event A, like this, right, in green. So in this case, for this any event, so for any event A, what we end up with is that the probability of A is, again, if you look at this, all we have to do is we basically have to say and add up what's the probability of A intersecting with B1, A intersecting with B2, A intersecting with all these, and then add them all up together, right? So in other words, we are going to add up all of the probabilities of A intersecting with any element of the partition and just go from n actually just, I guess, go all over n, right? So from n equals 1, 2, 3, 4, all the way up to however many partition elements you've got, right? So this is pretty much the way we can go about this. Alternatively, we could also substitute in an expression right here for this intersection if we want to do this using our conditional probability discussion, right? Where we understand that the probability of A intersect B, this can also be rewritten as the probability of A given Bn, right, times the probability of Bn, right? So either one of those two ways are basically just adding up over the partition all of these different spaces to get the total probability of A, right? So in this case, right, what we end up with is the probability of A. It's just the probability of A intersected with B1. Whoops, I didn't really want to write that as a subscript. I was trying to write it like this, B1, plus the probability of A intersected with B2, plus A intersect B3. But as you can see in this picture, it does not intersect at all, so that's going to be a 0. It doesn't intersect with B4. It doesn't intersect with B5. So I could tack those terms on here, but those are all 0, so they wouldn't contribute. So this is what we end up for this particular case. Right? Okay, so let's see how this could be used. So let's look at an example over here. So let's look at an elementary school, and we're interested in understanding who's buying lunch and who's bringing lunch to school. So this is actually motivated by my kids, actually. Their school, this is what you end up doing, right? Is you either buy lunch or you bring lunch. So let's consider a whole bunch of different events for this school. So this school goes from grades K, kindergarten, all the way up through 4th grade. So let's define maybe 5 events here. So A is just the event that the student is in kindergarten. B is the student is in 1st grade, blah, 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 all the way up to 4th grade, right? So these are sort of what grade you're in. This is kind of denoting events for each one of those different grades, right? Then let's look at, I don't know, let's break this up into boys and girls, right? So event F is that the student is a boy. Event G is that the student is a girl. And then lastly, let's look at these two down here. So H and I. Event H is that the student is buying lunch, and I is the student is bringing lunch, okay? So in this context of having this elementary school, let's look at a whole bunch of different questions we can ask. So first of all, let's just go ahead and draw a Venn diagram with events A through E on it. So that's actually pretty darn simple. Let's just go ahead and do this right now. So here's my sample space S, right? This is like the entire elementary school. And let's go ahead and write down all these events. Now, the nice thing is that you can't be in any of these grades simultaneously, right? You're either in kindergarten or 1st or 2nd or 3rd or 4th, right? So in other words, A through E form a partition of this space, right? So every student has got to fall into one and only one of these categories. So here's event A, B, C, D, and E, right? Okay, that's pretty easy. Okay, now how about F and G? Same thing. The school is all boys or girls, so this also is a secondary different type of partition that we could use, F and G. So the other way we could do this is maybe let's just go ahead and I'm going to draw F as maybe like this. Let me draw it in blue. So here's F, right? So blue is F. And then G, let's maybe do this in purple. That's just a different color, right? And again, I'm just trying to denote that, again, this is another partition. So F and G make a partition, and A, B, C, D, E make another partition, right? As you can kind of see here, okay? Now, let's go ahead and look at this. Let's say that we know the probability that a given student is going to buy lunch is 31.2%. And furthermore, we know the probabilities of grades K, 1, 2, and 3 buying lunch are given by these numbers, respectively, right? Now, what I'd like to look at is, can you use this information to show that there are no 4th graders that are going to be buying lunch, okay? So to do that, we basically need to come over here to our law of total probability, and now we can basically substitute this by looking and adding up all these probabilities over the partition. So in fact, let's go ahead and erase this, because really this is the situation we're looking at, right? So this is going to be the probability of, and in fact, we're not, it's not A, right? We're looking for what's the probability of buying lunch. That is H, right? This is event H. So I want the probability of H. So that is the probability of H intersected with all the elements of the partition. So in other words, this is the probability of H intersected with A, right? That's the first partition, plus probability of H intersected with B, plus the probability of H intersected with C, plus probability of H intersected with D plus probability of H intersected with E, right? So we are looking for this. I want to understand what is the probability that a fourth grader is buying lunch. Now, what we have is pretty much every other term in this expression. So we know this one right over here is the overall probability that a student is buying lunch. This is that 0.312 number, right? And then this here is the probability that a kindergartner is buying lunch. Well, that's given right here by, what do we say? It's 8 over 250. And then same thing. This is now the probability that a first grader is buying lunch. So this is 33 over 250. And then this one is what? It's 28 over 250. This guy here is 8 over 250. And basically, if you do the math here, you'll end up with the probability of H is buying lunch, right? Or sorry, a fourth grader is buying lunch. This is going to be 0. So there's no chance that a fourth grader is buying lunch here. So that is actually kind of interesting. In fact, this happened to the elementary school where my students my kids go to school, because the fourth graders were actually all on a field trip. Nobody was at school, so nobody was buying lunch, okay? So with that information, we can actually update our Venn diagram with events H and I, right? The event H, again, is buying lunch. I is bringing lunch. So really what this should probably look like is, let's do this in red. We know that there are no fourth graders buying lunch. So really, we could do something like this. Let's draw H like this. Right? So here is H. So this is the students who are buying lunch. We know there are kindergartners, first grade, second grade, third graders buying lunch, but no fourth graders. And furthermore, there are boys and potentially girls that are buying lunch. We just don't know what that distribution sort of looks like. So this is a kind of a Venn diagram that is now capturing all of this information that we've cooked up so far. Okay, now let's look at the last question here. Let's go ahead and ask ourselves, with this information, can we look at finding out what's the probability that a girl is going to buy lunch if we know that the probability of a boy buying lunch is 39 over 250. So again, we just need to come back over here to our law of total probability. And in fact, where can I find some space? Sorry, I'm running out of room for this. Let's just do it right here. Here's a fair bit of blank space. So we're looking for what is the probability of a girl buying lunch, right? So in fact, let's write it this way. Let's actually start by asking ourselves the question, what's the probability of buying lunch, right? Again, we can do this. So probability of buying lunch, right? So we did that over here by breaking it up and looking at the intersection over this partition, right, of the students, of the grade levels. But now what we can do is let's look at breaking this up over the partition of boys versus girls, right? So in other words, you could write this as the probability of H intersected with the boys, which was event F, right, plus the probability of H intersected with a girl, which is event G, right? So again, in this expression, what we're looking for is I want to know this term, right? What's the probability that a girl is buying lunch, right? This is the unknown. Do we know any of these other ones? Well, we know the probability of a boy buying lunch, right? That's given right here. This is 39 over 250, right? And now this, what is the probability that any given student is buying lunch, right? That is right here. We already said this. So this term here is 0.312, right? So if you do this, you can basically, again, solve for this. I can find the probability of a girl buying lunch. And actually, if you run these numbers, this is 0.156. So it's 15.6. And interestingly, this comes into the same thing, 39 over 250. So there's an equal chance of a boy or a girl buying lunch, right? So this is equally straddling the F and the G events. So there you go, an easy way to use the law of total probability for some of these situations. So, all right, so I think with that being said, this is probably a good spot to leave it. I hope you enjoyed the video, and if so, I also hope you'll consider subscribing to the channel. We've got more videos on probability and related topics coming up in the future. In fact, we're going to be talking about probability distributions and other types of specific distributions in the near future. So I hope we'll be able to catch you at one of these future discussions. So remember, the new videos come out every Monday, and hopefully we'll all be able to get together and learn something new together. So until then, I think I'll sign off. Talk to you later. Bye.